Now I want to come on to the probability density and distribution functions for a random walk process. The PDF of a random walk with parameter p at time t is based on the binomial distribution. It has this form. And we can plot the PDF for values of x in the range from 0 to 10 for time t equals 10, with parameter p set to 0.5. The CDF, the cumulative distribution function, follows a standard beta distribution. And again, we can plot this for a random walk with a particular probability parameter set to, for example, 0.5 at a time, say, t equals 10 for various values of x. This means that we can evaluate various event probabilities. For instance, supposing we wanted to find the probability that the particle motion process has moved at least 10 steps to the right after 20 seconds. We formulate it this way. Probability x of 20 time t equals 20 is greater than 10, given that x follows a particle motion process with probability parameters set to, for example, 0.5. We calculate that probability as being a little over 2%. We can look at the probability of the same outcome for random walks with varying drift levels. So here, for example, we're looking at the probability of x reaching a value of 10 or greater at time 20 if x follows a particle motion process with parameter p, where p is in the range from 0.5 to 0.95. And we can see that for the process with probability parameter at 0.5, the probability that x at time 20 will exceed 10 is around 2%, to a level very close to 1 as the drift in the process grows and the probability parameter is set to 0.9 or 0.95. It also means that we can ask more complicated questions, such as the following. Supposing after a certain number of seconds, 7 seconds, the process is at position x1. What's the probability that it will reach a position x2 after a further 5 seconds when t equals 12? So we formulate that question as follows. Probability that x12 is equal to x2, given that x7 is equal to x1. And x follows a particle motion process with probability parameters set to 0.5 in this case. And we'll look at various values of x2 in the range from 0 to 13 for various starting point levels, x1 being 1, 3, 5, or 7. This all sounds quite complicated, but it's actually quite easy to understand visually. This first chart, x1 is set to 1. So at time t equals 7, we're at position +1. And we can calculate the probabilities of ending up at 0, 2, 4, or greater at time t equals 12 from that starting point at time t equals 7. If our initial starting point is not 1, but 3 at time t equals 7, then the whole distribution is shifted to the right. There's now a non-zero probability of exceeding the level of 6 at time t equals 12. And as x1 increases from 3 to 5 and from 5 to 7, again, the distribution shifts further to the right. So there's now a non-zero probability of reaching a level of 12 or more after 12 time intervals. We can also, for example, simulate the proportion of time that the particle spends in positive territory. We simply generate a large number of paths from the particle motion process with parameter p set to 0.5, and then look at the number of those paths where the values are greater than 0. And when we do that, we find that the distribution follows what's known as an arc-sine distribution. There's a significant and high probability that the process will spend no time in positive territory. In other words, it'll move immediately into the negative zone and stay there. And there is almost equally large probability that it'll be in the positive zone throughout the entire process. And then there's lower probabilities that the process will spend some time in the positive zone with the remaining time spent below zero.